A planet hangs in our sky, one we have all but forsaken. This is Venus, our nearest planetary neighbor, a world so much like our own in its makeup that scientists once called it Earth's twin. And yet, for over 3 decades, no dedicated American spacecraft has traveled there. The last NASA probe to enter orbit around Venus arrived in 1989. That mission was named Magellan, and what it revealed was nothing short of extraordinary. Magellan's maps showed a planet blanketed by volcanoes, vast lava plains, and colossal mountains. A surface that looked geologically young and profoundly alien. The data it sent back posed fundamental questions about the very ingredients that allow a world to sustain life. Questions that we still cannot answer today. Despite this, for the next 30 years we looked elsewhere. As a steady stream of missions journeyed to Mars, Venus was left in the shadows. A world of immense scientific importance somehow became the forgotten sibling in planetary science. This is the story of why we turned our back on Venus, and why we are finally preparing to return. The Magellan spacecraft itself was assembled from spare parts, leftovers from other programs. Its radar was borrowed from the Voyager program, its propulsion system from Mariner, and its star scanner from Galileo. This was a mission shaped by tight budgets and political compromise, and against the odds, it was a spectacular success. Following a 15-month voyage through space, Magellan slipped into orbit around Venus in August of 1990. For the next 4 years, the spacecraft's synthetic aperture radar pierced the thick Venusian clouds, charting the surface with a level of detail never seen before. It achieved a resolution of about 300 feet per pixel and mapped over 98% of the entire planet. The world Magellan unveiled completely transformed our understanding of Venus. Its surface is a landscape dominated by volcanic activity. There are enormous shield volcanoes, some grander in scale than any on Earth. There are immense lava plains that run for thousands of miles. We saw strange, flat-topped mountains called pancake domes formed where thick lava oozed onto the surface and solidified. And we discovered coronae, unique circular fractures caused by plumes of hot material rising from the mantle and warping the crust from beneath. Perhaps the most startling discovery was that the planet appears to be geologically young. This is evidenced by its surface, which has fewer than 1,000 impact craters in total. For comparison, Earth's moon is scarred by millions of craters, and Mars has hundreds of thousands. The low number of craters on Venus points to a massive resurfacing event that must have happened sometime in the last several hundred million years. This finding was completely unexpected. Scientists had long presumed that Venus was geologically dead. Without plate tectonics or the lubricating effect of water on its crust, the planet should have become a static, inactive world billions of years ago. Instead, Magellan discovered signs of volcanic activity that was relatively recent and perhaps even ongoing. Among the most intriguing discoveries were the tesserae. These are vast, elevated plateaus like continents that stand high above the surrounding volcanic plains. Their surfaces are a complex maze of folds and fractures, suggesting they have been subjected to intense geological stress. One leading theory is that the tesserae are composed of ancient crustal rock, the oldest material on Venus, and a remnant of the world that existed before the Great Resurfacing event. If this is true, the tesserae could hold a record of Venus's distant past, a time when it may have had a different climate, and perhaps even oceans of liquid water. But for now, we simply don't know. Magellan's radar lacked the resolution to determine what the tesserae are made of, and no mission sent since has gathered any better data. Magellan continued its work until October 1994. At the end of its life, NASA commanded the probe to plunge into the planet's upper atmosphere, where it burned up and became part of the world it had revealed. And with that, the United States sent no more dedicated missions to Venus. Then, in August of 1996, a team of scientists made an announcement that would capture the world's attention. They claimed to have found microscopic fossils inside a meteorite from Mars. Known as ALH 84001, the rock had been violently ejected from the Martian surface by an asteroid impact millions of years earlier. After a long journey through space, it landed in Antarctica, where it was finally discovered in 1984. Deep within that meteorite were minuscule structures that, to some of the researchers, bore a striking resemblance to fossilized bacteria. The announcement ignited headlines around the globe. In response, NASA began planning a new wave of missions to Mars, all designed to hunt for more evidence of life, past or present. Ultimately, the claim did not withstand scrutiny. Deeper analysis revealed that the tiny structures could have been formed by purely geological processes with no biology involved. But the effect was profound and lasting. A powerful momentum had been created. Mars was now NASA's primary focus for planetary exploration. A flurry of missions followed, from Mars Pathfinder and its Sojourner rover in 1997 to Mars Global Surveyor that same year, all the way to the Perseverance rover and its Ingenuity helicopter in 2020. And NASA wasn't alone. Europe sent Mars Express, India launched its Mangalyaan orbiter, and China landed its Zhurong rover with the Tianwen-1 mission. Mars had become the undisputed center of the planetary science world. The funding, the research, the excitement, it all flowed toward the red planet, and Venus was left behind. This shift was also driven by practical realities. In almost every respect, Mars is simply an easier world to explore. Its atmosphere is thin, which makes landing a spacecraft relatively straightforward. The surface temperatures, while cold, are manageable. Rovers can operate for years, even decades. Solar panels can power them, and their electronics don't require elaborate thermal shielding. Communications are also reliable. Venus, on the other hand, is a world that destroys what we send to it. To this day, the longest any lander has ever functioned on its surface is just over 2 hours. The combination of crushing pressure, searing heat, and a corrosive atmosphere makes conventional exploration almost impossible. Solar panels are useless beneath the thick clouds, and standard electronics fail in moments. Even components that are specially hardened for the conditions give out within minutes or hours. From a purely engineering perspective, focusing on Mars makes a certain kind of sense. But science is supposed to be about tackling the most important questions, not just the ones that are easiest to answer. And the questions Venus poses are profound. Why is Venus the way it is today? This is the central mystery, a question that is vital not just for understanding our neighboring planet, but for understanding our own. It's about grasping what makes a planet habitable in the first place, and what happens when a world that might have been a paradise instead becomes a hellscape. Because all the evidence suggests that Venus wasn't always this way. The key clue lies in its atmosphere, specifically in the ratio of heavy water to normal water. Heavy water is a form of H2O in which a deuterium atom, a heavier version of hydrogen with an extra neutron, replaces one of the regular hydrogen atoms. Because it is heavier, deuterium does not escape into space as easily as normal hydrogen. The atmosphere of Venus has a much higher concentration of heavy water than Earth's does, about 150 times higher. This strongly indicates that Venus once possessed a great deal more water than it has now. Over billions of years, the lighter, normal hydrogen was lost to space, leaving the heavier deuterium behind in ever greater concentration. How much water are we talking about? Perhaps enough to have covered the entire planet in oceans. And if Venus once had oceans, it must have also once had a climate that could support liquid water. That would mean temperatures between 0 and 100 degrees Celsius. It would mean an atmosphere that wasn't choked with carbon dioxide and clouds that weren't laced with sulfuric acid. In other words, Venus may have once been a world much like our own. So what happened? How did a potentially habitable planet turn into the hottest place in the solar system? The answer lies in a process known as the runaway greenhouse effect. Here's how it is thought to have worked. Being closer to the sun, Venus naturally receives more sunlight than Earth. But early in the solar system's history, the sun was about 30% dimmer than it is today, which means early Venus may have enjoyed temperatures similar to Earth's. As the sun grew brighter over time, however, Venus began to warm. This caused water from its oceans to evaporate into the atmosphere. Water vapor is a powerful greenhouse gas. It traps heat. So as more water entered the atmosphere, the planet's temperature rose even higher, which in turn caused more water to evaporate. This created a positive feedback loop. More heat led to more water vapor, which led to more heat. The cycle likely continued until all the planet's water had been boiled away into the atmosphere, wrapping Venus in an incredibly dense, hot blanket of steam that trapped the sun's energy. At this stage, the atmosphere of Venus would have been thick with water vapor. High-energy ultraviolet light from the sun would have split these water molecules into their component parts, hydrogen and oxygen. The hydrogen, being very light, escaped into space. The oxygen, meanwhile, would have reacted with rocks on the surface or combined with other gases in the atmosphere. Over hundreds of millions of years, the planet's water was completely lost. First boiled into the atmosphere, then stripped away into space, leaving a parched, desolate world. At the same time, carbon dioxide began to build up. On Earth, carbon dioxide is naturally pulled from the atmosphere by a cycle involving rock weathering and plate tectonics. Rainwater mixes with atmospheric carbon dioxide to form a weak carbonic acid, which then reacts with surface rocks. Over geologic time, these carbon-rich minerals are carried into the mantle at the boundaries of tectonic plates, effectively locking the carbon away. But this entire process depends on liquid water. Without water, there is no weathering. And without weathering, carbon dioxide has nowhere to go. Volcanoes continued to pump carbon dioxide into the atmosphere, but with no mechanism to remove it, the gas accumulated. The result is the Venus we see today, a planet with an atmosphere that is 96% carbon dioxide, driving a greenhouse effect so extreme that surface temperatures soar past 450 degrees Celsius, hot enough to melt lead. This is the general scenario that most scientists believe explains the transformation of Venus. But the details remain uncertain. When exactly did this runaway greenhouse effect start? Did it happen early in the planet's history, or did Venus remain habitable for billions of years? Did it ever truly have oceans, or was it a steamy, hostile world right from the beginning? These are not just academic questions. The answers have major implications for how we think about planetary habitability across the universe. Surveys of exoplanets have already discovered thousands of worlds orbiting other stars, and many of these are similar in size to either Earth or Venus. A significant number of them orbit within what astronomers call the habitable zone, the region around a star where conditions might be right for liquid water to exist on a planet's surface. The problem is we can't actually see the surfaces of these distant worlds. We can measure their size, their mass, and the path of their orbit. In some cases, for the brightest and clearest examples, we can even get a sense of what their atmospheres are made of. But how can we tell if a given exoplanet is more like Earth or more like Venus? How do we distinguish a habitable world from a hellish one? The truth is, right now, we can't. We can't because we don't fully understand the fundamental differences that set Earth and Venus on such divergent paths. We don't know where the tipping points are in the evolution of a planet's climate. We don't know what warning signs to look for that tell us a planet has passed the point of no return. Venus holds the key. By studying our nearest neighbor, we can learn how to interpret the data we gather from these faraway worlds. It can teach us how common planets like our own truly are. It can help us answer one of the biggest questions of all. Is life in the galaxy a rare accident, or is it abundant? And for 30 years, we have been ignoring the one planet that could help us find out. Then, in September 2020, an international team of scientists announced the potential detection of a gas called phosphine in the clouds of Venus. The finding was based on observations from two separate telescopes, the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter Submillimeter Array in Chile. Both instruments had registered a spectral signature at a specific wavelength that corresponded to phosphine gas. The announcement immediately set off a firestorm of controversy. The controversy arose not from the gas itself, but from where it was found and what its presence might mean. On Earth, phosphine is produced almost exclusively by life. To be specific, it is made by anaerobic bacteria that live in environments with little to no oxygen, such as the digestive tracts of animals. These microbes generate phosphine through metabolic processes that are still not fully understood. Crucially, there are no known non-biological processes on our planet that create phosphine in any significant quantity. Not volcanism, not lightning, not atmospheric chemistry. Life is the only substantial source. And so, the detection of phosphine on Venus raised a startling question. Could there be life floating in its clouds? The idea is not as outlandish as it may seem. The surface of Venus is hostile to any life we can imagine, but 50 kilometers up, the conditions are dramatically different. There, the atmospheric pressure is the same as at sea level on Earth, and temperatures hover between 20 and 30 degrees Celsius. Water droplets exist in this zone, although they are suspended within clouds of concentrated sulfuric acid. For years, some scientists have speculated that microbial life could survive in such a niche, protected inside the liquid droplets using sulfur chemistry for energy and drifting indefinitely on the high-altitude winds. It was an extraordinary claim, and one that requires extraordinary evidence. But almost as soon as the discovery was announced, that evidence began to crumble. Almost immediately, other researchers began reanalyzing the telescope data, and they found problems, processing errors, statistical uncertainties, and the possibility that the signal was actually from sulfur dioxide, which has a spectral signature very similar to phosphine. Some subsequent analyses concluded that there was no phosphine at all. Others suggested that if the gas was present, it was in far smaller amounts than originally claimed. The search for independent confirmation from other observatories yielded nothing. NASA's SOFIA Airborne Observatory saw no trace of it. Neither did the Infrared Telescope facility in Hawaii. A review of archival data from Europe's Venus Express spacecraft, which orbited the planet from 2006 to 2014, also showed no signs of phosphine. The scientific community was now divided. One camp maintained that the phosphine signal was real and demanded an explanation. The other argued that the detection was fundamentally flawed and that the entire claim should be dismissed. Then in 2024, the story took another turn. Using the same James Clerk Maxwell telescope, the original team announced they had detected phosphine again. But this time they had gathered more data, achieved a better signal-to-noise ratio, and used improved analysis techniques. And their new findings included something else: the presence of ammonia in the clouds. Ammonia is another gas that, based on our understanding of Venus's oxidizing atmosphere, simply shouldn't be there. Like phosphine, it would be destroyed quickly by chemical reactions, and like phosphine, its primary source on Earth is life. But ammonia also has a particularly interesting property. When dissolved in sulfuric acid, it acts as a buffer. It neutralizes some of the acid. So if microbes were living inside those acid droplets, producing ammonia would make their immediate surroundings more hospitable. They would essentially be engineering their own environment, creating a livable pocket in the clouds through the byproducts of their own metabolism. Now, this is not proof of life on Venus, not even close, but it does point to something strange happening in those clouds, something our current models of the atmosphere cannot explain. Several non-biological hypotheses have been put forward. One is that volcanoes are venting phosphides, mineral compounds that contain phosphorus in a chemically reduced state. Another idea points to chemical reactions on the surface of dust particles, or perhaps chemistry driven by lightning. A final possibility is some exotic atmospheric process we have yet to imagine, but none of these explanations are truly satisfying. The volcanic theory would require immense eruptions of a very specific and unusual kind of magma. The photochemistry model simply can't produce enough phosphine to match what was observed. And lightning on Venus, if it even happens, appears to be too rare and weak to be the cause. The most honest answer is that we simply don't know. We don't understand the chemistry of Venus's atmosphere well enough to dismiss a non-biological source, and we certainly can't confirm a biological one without a great deal more evidence. What we truly need is to go there. We need to sample the clouds directly to measure their chemical makeup on site, and to watch the atmosphere's dynamics and chemistry unfold in real time. And that brings us back to the fundamental problem. For decades, we have not returned to Venus. We do not have the tools in place to answer these questions. We don't have the missions, we don't have the data, until now. In June of 2021, NASA made an announcement that sent a shockwave through the planetary science community. The agency had selected not one, but two new missions for its Discovery program, and both of them were going to Venus. The first is called Da Vinci Plus, which stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging Plus. This mission consists of a probe designed to plunge through the Venusian atmosphere, taking detailed measurements all the way down to the surface. It will analyze the composition of the atmosphere, measuring noble gases, their isotopes, and other trace elements. As the probe descends through the clouds, its cameras will capture images of the surface in a resolution far greater than anything achieved before, while infrared spectrometers identify the minerals on the ground below. The primary goal of Da Vinci Plus is to answer the question of when Venus lost its water. By measuring the ratios of different noble gas isotopes, scientists can reconstruct the planet's thermal history. When gases were released from its interior, when its atmosphere began to escape, and whether it remained habitable for billions of years or lost its oceans early on. Da Vinci Plus will also study a specific region called Alpha Regio, one of the planet's tesserae. If these ancient highlands contain minerals that can only form in the presence of liquid water, it would be the first direct proof that Venus once had oceans. If, on the other hand, the rocks are purely volcanic, it would point to a much drier history. The probe is expected to survive for about an hour as it falls. Once it impacts the surface, its instruments will fail. But in that single hour, it will gather more direct data about the atmosphere than we have collected in the last 40 years combined. The second mission is named Veritas, for Venus emissivity, radioscience, INSAR, topography, and spectroscopy. This is an orbiter equipped with a state-of-the-art radar system, far more advanced than the one carried by Magellan. Veritas will map the entire planet in 3 dimensions, creating high-resolution topographic maps down to about 30 feet per pixel. It will use infrared spectroscopy to determine the composition of the surface and measure the planet's gravity field to probe its internal structure. The Veritas mission will hunt for active volcanoes, look for signs of recent lava flows, and search for deformations in the crust that could indicate magma moving just below the surface. It will study the tesserae in unprecedented detail, finally determining if they are made of sedimentary rock, volcanic rock, or something else entirely. Veritas is designed to answer the geological questions that Magellan couldn't resolve. How often do volcanoes erupt? Is some form of plate tectonics at work, or has the planet's geology evolved through a completely different process? What is its internal structure and how much heat is escaping from its core? Both missions are slated for launch in the early 2030s, with Da Vinci Plus going first and Veritas following a few years later. Together they promise to revolutionize our understanding of Venus, and they are not the only ones going. In 2021, the European Space Agency selected a mission called EnVision, an orbiter designed to work in tandem with Veritas. EnVision will be equipped with its own radar for surface mapping and spectrometers to analyze the atmosphere and surface composition. Its strategy will be to focus on specific targets, conducting highly detailed surveys of key regions rather than aiming for global coverage. EnVision will also carry a radioscience experiment to measure Venus's gravitational field with extreme precision. This will reveal variations in density deep inside the planet, helping to determine if it has a liquid core, a solid mantle, and distinct layers like Earth. So that is 3 missions from 2 different space agencies, all scheduled to arrive at Venus within a few years of one another. This represents a fundamental shift in priorities. After 3 decades of neglect, Venus is suddenly back in the spotlight. The scientific community has finally recognized what was lost during the years of our singular focus on Mars. And there are still more missions in the works. Russia's space agency has proposed Venera D, a combined orbiter and lander planned for the 2030s. India's space agency is preparing its own Venus orbiter mission, with a launch scheduled for 2028. Even private companies have begun to explore the possibility of atmospheric missions using balloons or floating platforms. The Renaissance has begun, but sending missions to Venus means solving problems that don't exist at Mars or anywhere else in the solar system. The most fundamental challenge is simply survival. Down at the surface, the temperature exceeds 450 degrees Celsius. The atmospheric pressure is 92 times that of Earth. The atmosphere itself is corrosive. Clouds of sulfuric acid will devour most materials. At such high pressures, carbon dioxide becomes a supercritical fluid, something that is neither gas nor liquid, with bizarre thermal properties that make managing heat incredibly difficult. In these conditions, conventional electronics fail within minutes. Silicon-based computer chips stop functioning at around 150 degrees Celsius. Solder melts, circuit boards degrade, and batteries die. Mechanical parts seize up. Optical windows fog over or crack. The Soviet Venera landers of the 1970s and 80s solved this problem through brute force. They were essentially armored pressure vessels built with thick walls and layers of thermal insulation. Inside, they were packed with special salt blocks designed to absorb heat. Their instruments were simple and mechanical, built to function just long enough to transmit data before they inevitably failed. Even with these extreme measures, the longest any lander ever survived was 2 hours. Most were silenced much sooner. Modern technology, however, offers new solutions. Materials like silicon carbide can be used to make semiconductors that operate at temperatures above 500 degrees Celsius. These are already used in aerospace applications that require extreme heat resistance. At NASA's Glenn Research Center, engineers have developed silicon carbide integrated circuits that have run for more than 500 hours inside 500-degree ovens. In simulated Venus surface conditions, some of these chips have continued to function for a full 60 days. This represents an improvement of more than 100 times over conventional electronics. That's a long enough lifespan to enable missions that could operate on the surface for weeks or months, instead of just minutes. The catch is that silicon carbide electronics are still very primitive compared to standard silicon chips. Their complexity is roughly on par with computers from the 1970s. You cannot build a sophisticated rover or a suite of complex scientific instruments with this technology. At least, not yet. So for now, surface missions will remain limited. Landers will carry simple instruments, temperature sensors, pressure gauges, perhaps a drill to sample the surface. The goal isn't extensive exploration, but targeted investigation. Answering specific questions, measuring key parameters, and gathering the kind of data that can't be collected from orbit. Missions to the atmosphere face a different set of challenges. The clouds are far less hostile than the surface. Temperatures and pressures there are manageable. The main difficulty is navigation. Venus itself rotates very slowly, completing one turn every 243 Earth days. But its atmosphere rotates much faster. At cloud top level, winds can reach 360 kilometers per hour, faster than the most powerful hurricanes on Earth. Any probe or balloon sent into the atmosphere would be whipped around the entire planet in just 4 days. Maintaining control in such an environment is nearly impossible. You simply go where the wind takes you. This isn't necessarily a problem, but it does demand a different approach to mission design. Instead of rovers that can be directed to specific targets, you would use floating platforms that drift with the atmospheric currents. Instead of landing at a pre-selected site, you would descend wherever the winds happen to carry you. Instead of long-term operations on the ground, the focus shifts to atmospheric measurements and remote sensing. NASA has explored concepts for solar-powered airplanes that could fly indefinitely in the upper atmosphere. The idea is to have them cruise at an altitude of 50 to 60 kilometers, where the environment is relatively mild. The aircraft would be covered in solar panels on both the top and bottom. Because Venus reflects so much sunlight that the light coming up from below is almost as intense as the direct sunlight from above. The aircraft would ride the fast-moving winds circling the entire planet every few days. It would carry instruments to study atmospheric chemistry and cloud structure, and it could use radar and infrared imaging to map features on the surface. It could even act as a communications relay for probes on the ground. A mission like this would be technically difficult, but it is feasible, and it would provide the kind of long-term, close-up observations that an orbiter simply cannot. The real bottleneck, however, is cost. Missions to Venus are expensive because they demand custom-built engineering solutions. A Mars rover can be built using commercial electronics that have been specially hardened against radiation. A Venus lander, by contrast, requires a completely different kind of technology. Missions to Mars can draw on decades of experience and proven designs. But for Venus, we are essentially starting from scratch each time. This has created a vicious cycle. Because Venus missions are expensive, they are rarely chosen for funding. Because they are rarely chosen, the technology needed to explore Venus doesn't advance. And because the technology doesn't advance, the missions remain expensive. To break this cycle requires a sustained commitment. A series of missions, each building on the successes of the last. It means developing standardized platforms that can be reused and making incremental advances in components and systems. This is precisely the path we followed with Mars. The early missions were costly and fraught with risk. Many of them failed. But over time, as experience grew, costs came down and the rate of success went up. Today, sending a mission to Mars is almost routine. Venus could be set on the very same course if we commit to going back. If we decide that answering fundamental questions about planetary evolution and habitability is worth the investment. And it appears that for now, the decision has been made. The Da Vinci Plus and Veritas missions represent that commitment, and Envision reinforces it. The question now is whether this is just a brief moment of renewed interest, or the beginning of a long-term, sustained program of exploration. In the end, the most profound reason to study Venus has less to do with Venus itself and everything to do with Earth, and with the thousands of new worlds we are now finding around other stars. By all accounts, Earth and Venus should be twins. Venus is 95% of Earth's diameter and has 82% of its mass. Their densities are nearly identical. They were born in the same part of the solar system from the same raw materials and at roughly the same time. And yet their destinies could not have been more different. One world became a vibrant biosphere. It developed oceans teeming with life, continents covered in forests, and an atmosphere that breathes. Its climate, despite ice ages and warm spells, has remained remarkably stable for billions of years. The other became a furnace. To understand why these two similar planets ended up on such profoundly different paths is to confront one of the most important questions in planetary science. The answer tells us which factors truly determine habitability, what conditions are essential for life, and what thresholds separate a paradise from a wasteland. These are the very questions we are now desperately trying to answer for worlds we can never hope to visit. The study of exoplanets has revolutionized our understanding of the cosmos. We have found thousands of planets orbiting other stars, many of them rocky worlds like Earth and Venus. Many of these orbit within the habitable zones of their stars, where temperatures could theoretically permit liquid water. But we can only measure a few of their basic properties: size, mass, orbital period. For the largest and brightest examples, we can sometimes get a sense of their atmospheric composition. But we cannot see their surfaces, we cannot measure their atmospheric chemistry in detail. We cannot determine if they are habitable or hostile. To interpret the limited data we collect, we need a reference, a framework for understanding how rocky planets evolve and what signatures indicate a world might harbor life. Venus provides that reference. It shows us what happens when a planet passes a climatic tipping point, when greenhouse warming becomes irreversible, when oceans boil away and the atmosphere transforms into a crushing blanket of carbon dioxide. If we can understand Venus, we can learn to recognize the warning signs in our observations of these distant worlds. We can then use that knowledge to estimate which of these worlds are more like Earth and which are more like Venus. We can begin to assess whether a planet orbiting in the habitable zone is actually habitable, or if it is a scorched wasteland that only appears to be in the right place. This has profound implications for the search for life beyond our solar system. If planets like Venus turn out to be common, then true Earth-like worlds may be rare. If the tipping point for a runaway greenhouse effect is narrow and easily crossed, then habitable planets are precious outliers. And if the fate of Venus was determined by subtle factors we have yet to identify, then predicting the habitability of a distant world will require far more information than we currently have. But the lessons from Venus also strike much closer to home, informing our understanding of Earth's own distant future. Climate models predict that our world will eventually suffer its own runaway greenhouse effect. This won't be caused by human activity, but by the natural aging of the sun. As our star gets older, it grows brighter. In about 1 billion years, its energy output will have increased enough to push Earth past the same tipping point. Our oceans will boil, the water vapor will trap heat, and the hydrogen will escape into space. Earth will become another Venus. This outcome is inevitable, but its timeline depends on details we don't yet fully understand. How efficiently is water vapor lost to space? What kinds of feedback loops might slow down or accelerate this transition? And at what precise temperature does the process become irreversible? Venus has already completed this transition. By studying it, we can learn what to expect, how quickly such a change happens, what the final state of the planet looks like, and whether there might be intermediate stages where life could briefly persist in refuges before the final collapse. This knowledge is more than a matter of academic curiosity. Understanding Earth's long-term fate helps us appreciate the temporary nature of our own environment, the narrow window of habitability that we currently occupy, and the profound fragility of the systems that support all complex life. It also provides vital context for evaluating shorter-term climate change. Human-caused global warming will not turn Earth into Venus. That is not a realistic outcome. The runaway greenhouse effect is a specific process that requires conditions our own carbon dioxide emissions cannot create. But studying how greenhouse effects can amplify and become self-reinforcing is essential for modeling how any climate system responds to stress. Venus teaches us what a runaway state looks like. Earth teaches us what stability looks like. Together, they define the very boundaries of habitability for rocky planets. And we can only truly learn these lessons by going there, by measuring its atmospheric chemistry directly, by analyzing the composition of its surface, by observing its volcanic activity and atmospheric dynamics in real time. Remote sensing from Earth has its limits. What we need are spacecraft orbiting Venus, instruments descending through its atmosphere, probes landing on its surface, and long-term observations that can track how the planet changes over months and years. That is why Da Vinci Plus, Veritas, and Envision matter so much. They are not just missions to another planet. They are investigations into the fundamental questions of how worlds evolve, what makes them habitable, and where our own planet fits in the cosmic spectrum of possibilities. These are questions that cannot be answered by ignoring Venus for decades. They cannot be answered by focusing exclusively on Mars just because it is an easier target. They require a sustained, systematic study of the planet that became our opposite twin. After 30 years, we are finally going back. But this cannot be the end of the story. These 3 missions will provide a tremendous amount of new data, but they are only the beginning. What is needed is a long-term program of exploration, Multiple orbiters, multiple landers, atmospheric probes and balloons, and eventually sample return missions that bring pieces of Venus back to Earth for analysis in our laboratories. We need the science of Venus to become routine, not extraordinary. We need missions launching every few years, each one building on the discoveries of the last. We need to develop the technology and expertise for sustained exploration. Mars has shown us how valuable this approach can be. Decades of missions have given us a comprehensive understanding of that planet's history, its geology, and its potential for life. Venus deserves the same level of attention because the questions it raises are just as important. Perhaps even more so given its eerie similarity to Earth and its direct relevance to understanding the countless new worlds we are now discovering. A planet hangs in our sky, one we have all but abandoned. For 3 decades, we chose Mars instead of Venus. We chose convenience over consequence. We chose the familiar challenge over the profound one. We chose to search for fossilized microbes in ancient lake beds, rather than understand how our own twin planet became a vision of hell. This choice was not entirely without reason. Mars is, by all measures, an easier world to explore. Its engineering challenges are well understood. The chance of finding traces of past or present life, however small, is real. And the scientific value of studying Mars is undeniable. It is a worthy target for exploration. But Venus matters more, because Venus tells us about the future of Earth. It tells us about the stability of climates that can support life, and it tells us just how rare worlds like our own might be in the universe. And in making that choice, we lost time. 30 years of missions that were never flown, 30 years of data that were never collected, 30 years of progress in understanding how planets evolve. Progress we postponed simply because we chose to look away. The consequences of this neglect are real. To this day, we do not know when Venus lost its oceans. We do not know if it was habitable for billions of years, or if it was doomed soon after it formed. We do not know if the tesserae are the remnants of ancient continents or vast volcanic highlands. We do not know if its volcanoes are still active today. And we have no confirmed explanation for the phosphine and ammonia that have been detected in its atmosphere. Every one of these is a question that can be answered, and they could have been resolved by the missions we chose not to build. But now, the tide is turning. Da Vinci Plus, Veritas, and Envision represent a renewed commitment to the exploration of Venus. They are a recognition that we made a mistake by turning our back on this world for so long. When these missions arrive in the 2030s, they will map the surface in unprecedented detail. They will measure the composition of the atmosphere with a precision never before achieved. They will probe the planet's internal structure and hunt for active volcanoes. They will study the tesserae and finally determine their origin. And in answering old questions, they will undoubtedly raise new ones. Every mission to Venus has. The more we learn about this world, the stranger it becomes. Its atmosphere is more complex than our models predict. Its surface is younger than it should be. Its chemistry does not behave as we expect. Venus is not a solved problem. It is a mystery that only deepens with each new piece of information. Perhaps that is why we looked away for so long. Mars is a world we can comprehend. Its history is largely written in stone, waiting for us to read it. Venus is chaotic, hostile, and confounding. It resists our attempts to make sense of it. But science is not about studying what is easy. It is about studying what is important. And few questions are more important than understanding how planets like our own evolve, what determines their fate, and where Earth itself fits into that grand story. We are going back to Venus because we must, because the questions demand answers, because 3 decades of neglect was long enough. The next chapter in the exploration of Venus is about to begin, and perhaps this time we will not turn away. Perhaps this time we will commit to a sustained investigation, building the knowledge and the technology needed to truly understand our mysterious twin. Perhaps we will finally give Venus the attention it has always deserved. The planet waits, patient and unchanging, wrapped in its clouds of sulfuric acid, holding secrets that could reshape how we see worlds across the universe. It is time to go back. What we understand so far is fragmentary, like pieces of a puzzle scattered over decades of intermittent observation. The Soviet landers offered fleeting glimpses of the surface. Magellan gave us a map of the terrain but could not explain why it looked so young. Atmospheric studies detected strange chemicals but could not reveal their origin. Every answer has only led to more questions. Da Vinci Plus will plunge through the atmosphere, measuring its composition and photographing the surface. Veritas will orbit for years, watching for volcanic eruptions and mapping every tessera. Envision will fill in the finer details, targeting specific features with high-resolution instruments. Together, they will help us understand when Venus died, how fast its transformation occurred, and if it was ever truly habitable. They will reveal the processes that shaped its surface and probe the question of whether life could exist in its clouds. But they will not answer everything. No 3 missions ever could. Venus will remain a mystery, a world that is still strange, still resistant to simple explanations. And perhaps that is how it should be. The universe does not give up its secrets easily. We learn by observing patiently, by measuring carefully, and by investigating with persistence. For 30 years, we walked away from Venus. That was a mistake. But it is a mistake that can be corrected. We are going back, not because it is easy and not because it is popular, but because to understand Venus is to understand Earth. It is to understand what makes a world habitable and what we risk losing if we are not careful. The missions will launch in the coming years. They will arrive at Venus in the 2030s, and for the first time in decades, we will watch as new data streams back from our forgotten twin. The planet that became hell will finally tell us how it died. And in doing so, it will teach us how to recognize life when we find it elsewhere and how to protect it here at home. It will teach us to appreciate the narrow circumstances that make Earth, for now, a paradise in the void. Venus waits in the sky, patient, eternal.